Hello everyone. Today I am going to discuss on introduction to IC fabrication. In my earlier videos, I have shown you that it is a continuous process where the basic fabrication process steps that has been discussed, where we need to begin with a substrate, and the substrate, it is to be made of most likely with silicon material. Why silicon material? What are the advantages of using silicon material? What are the other disadvantages of other material if we use as a substrate while making an IC? I have discussed already. But to brief you or to recapitulate, I must say that silicon material, it is much more available in today's world naturally. Along with that, if we want to make any kind of dielectric material, silicon would be the best one for making or for providing the dielectric material at lower cost compared to other materials. Followed by other steps where the application of photoresist, where the photoresist it is generally made of two, hardened and softened photoresist, and then the whole process in figure D, as you can see that the whole setup, it need to be incidenting to the UV light, that is sunlight. Due to the moisture content, automatically the silicon will be formed as a silicon dioxide, as we all know, and it will act as a insulating material over which the photoresist need to be placed or covered. And then when we are exposing this to UV light, automatically what will happen, the exposed areas will become soluble so that they are no longer resistant to the etching solvents. Next, in this particular slide, we can see in the figure E where I told you that the hardened photoresist will be there as it is, whereas the softened photoresist, they will be chemically evaporated, they will be chemically etched away by means of HF acid or dry etch plasma. Why we are mainly focusing on this region is because we need to have the target oxide window over which we need to access the channel, because the moment we are talking about an IC, let me tell you one thing, for a VLSI beginners, IC cannot be made on a abruptly. IC can be designed step by step process. So we need to begin with simple transistors, and the moment we're talking about simple transistors, we're generally talking about digital transistors like field effect transistors. If we talk about field effect transistor, we know that the basic three electrodes are there: source, drain, and in between of these two electrodes there has to be channel. So through the channel we need to connect the gate electrode. So that is why to have a bare oxide window we need to follow this processes, followed by which we need to to access that particular channel, to access that particular substrate, that is body, what we have to perform? Etching. If you can see this one, etching. So we need to perform etching. It is certain process by means of which that unwanted portion it can be removed from that particular surface, just to have a bare oxide window over which we can actually deploy the gate electrode. Okay, so finally the remaining hardened photoresist, also in the last figure of G, we can see that the hardened photoresist can also now be stripped off from SiO2 surface by using another solvent. So finally it will look like this type, where the whole substrate is showing over there, and after following all the processes we can get to see the substrate like diagram like this type. Okay, we call it in VLSI technology, it is as a single pattern transfer. Very important topic of a single pattern transfer on the silicon dioxide. Okay, now if you use this fabrication process flow, so we can easily design a NMOS transistor. Let us talk about NMOS today, where it is a very basic one. We want to design NMOS or PMOS. So why we call it NMOS or PMOS? We all know that it is simply because of the polarity of the carriers. Okay, which are the majority carriers? Depending upon that, the carrier transportation used to move from the channel from one side to the other side. Now let us assume that if the majority carriers are of electrons, so let us talk about, we can design it is of a NMOS. Now if we design a NMOS transistor, we need to know that the substrate need to be made up of p type. This is a basic one, okay, and due to that particular process of recombinations and all, we can easily design it. If it is a n-type substrate, we can always go for the p-type designing. Okay, so here the process will always starts with oxidation, as I have discussed earlier also. Then SiO2 layer will be created, as I have discussed in the earlier slides, on silicon surface. Then the filled oxide will come into the picture, where filled oxide will be selectively etched. Why selectively etched? Because we need to know that where exactly I need to put my source electrode, drain electrode, and the channel over which the gate electrode can be formed. After doing this etching, then finally we need to pattern. Pattern means layering. In VLSI technology, we used to term it as a pattern. Then patterning of a thin, high quality oxide layer on the top. You can see here in the last figure, I am browsing, I am just rotating my mouse tip, where you can see the thin oxide, that is the dark shaded, that the diagram is there, the thin oxide will be layered. In the coming slide, we can see also another darker shade is there in the figure E. We call it as a polysilicon. Polysilicon is very important. Polysilicon is mainly placed or layered due to the placing of metal electrodes. It is used to connect both gate electrodes, if we talking about of NMOS and as well as the PMOS, in the same substrate. Talking about of making a CMOS, because CMOS, it is a complementary MOSFET, where in the same substrate NMOS and PMOS both can be accommodated. And finally, in the figure of F, we can see that after impurity doping, the polysilicon layer is actually patterned and then finally also selectively etched. Same process. Why you have to selectively etched is because we need to know that the gate electrode cannot be directly connected to the channel, so that is why the gate electrode need to be insulated. So that is why the only portion on the channel window, it need to be remaining as it is. As you can see, a slightly portion of the polysilicon layer is left off, where the other polysilicon layers are actually getting stripped off, because the source and the drain regions will be directly connected to the these two sections, where the gate electrode, it can be connected over the polysilicon terminal, or we can say polysilicon layer. Okay, and the last figure, you can see it's a very beautiful figure, where in figure G we can actually accessing a proper window in the channel, where we can see that the gate oxide is not covered by the polysilicon, also etched away. Why is because we need to have the proper window in the channel. We need to access the bare window, or through which here I am marking my mouse. Through here the source, through here the drain electrode can be you can be designed, and from the over the polysilicon layer we can design the gate electrode. So this is how finally we can make a NMOS. Now don't worry about the placing of the source and the gate source and the drain electrode, because drain and source, it can be swapped, no issues on it. What will happen is that the flow of the current transposition from one side to the other side through the channel will be just flipped away. That's simple, that much, because only that swapping it can be done, but the whole process need to be understood through this particular diagram. So you need to understand the whole diagram step by step, because it's very very important to understand the fabrication process of a NMOS. Now if you talk about the continuous process, where we can also go in for the finally the diffusion, and after diffusion we need to go for the implantation, and finally in the implantation we can see that the N plus insulating oxide layers are also etched partially to provide the S and D contact, that is the source and drain contacts, which is need to be done in the figure J. And then lastly we can see that the entire surface is finally covered with the evaporated aluminum, which will form the interconnections, and the metal layers, we can finally deploy the metal collections of aluminum or any other metals. It can be placed through that particular junction, just to make the connection of source as well as the drain and the gate connections. I hope this video is quite subjective to your matter. In the next class onwards, we will discuss about the IC fabrication of the total CMOS. Thank you.